Hello, this is a video on mathematical induction. I'd like to show you 2 or 3 types of mathematical induction, and we're going to prove some statements with them as well. Let's have a look at this. So here's the principle of induction, and I'm presenting this as a theorem, which is a word for a true bit of mathematics. It talks about a family of statements, Pn, and the phrase here is that they're indexed by the natural numbers, by which I mean that there is a statement P0, whatever it is, some statement about the number 0, I suppose, and then P1, P2, P3, and so on and so on and so on. For every natural number, there's a statement starting at 0. And then the principle of induction says, suppose that P0 is true, and, so this one is true, and suppose that for any n, if Pn is true, then Pn plus 1 is also true. And I mean here any n in the natural numbers, so for any n that could be 0 or 1 or 2, and so on. So it says, if Pn is true, then Pn plus 1 is also true. So if P0 is true, then P1 is true, and if P1 is true, then P2 is true. If P2 is true, then P3 is true, and so on and so on and so on for any n. Then, as a result, says the principle of induction, Pn is true for all natural numbers n. And the thing that you might have in mind is this chain of statements where the very first one, P0, is true, and then each one follows from the previous one so that they all are true afterwards. That's being presented as a theorem or a principle or something that I hope just seems true, that if you have this chain of consequences and you have the first thing being true, then all of them are true. We're going to see a proof later on in this section, although we'll talk about the proof when we get there. But first let's try this out. In order to try this out, I need some notation. This course contains a lot of notation and definitions. And one thing I'd like to show you is sums of numbers, or functions of those numbers. So here's an expression you might have met before. It says the sum from k equals a up to b of f of k, where f is some function, and that means that you take the values from a to b inclusive, you apply the function to each of those numbers, and you add those up. So I have f of a plus f of a plus 1 plus f of a plus 2 plus 9 all the way up to f of b. And that's some notation that we're going to use in our statement in a second. When you see these typeset in line, they're sometimes presented like this, with the start condition and the stop condition sort of not standing below and above the capital sigma sign. So that's some other way that they're sometimes presented. And that's a sum. There are other notations for sums that you might meet, or extensions of this. So we might sum over the values in a set S if we want to look at particular values, in which case we're only plugging in particular values into the function, the ones that are in S. And sometimes that might even just be described in words. So I've seen people use notation like this, where they just say P prime to mean, evaluate this function on all of the prime numbers and add up the results that you get afterwards. But I'm getting ahead of myself a bit. Oh, I should say that empty sums so things like if the stop condition is less than the start condition, then that sum's understood to be 0. It's a sum with no terms, which by convention we say is 0. Not to be confused with the sum from k equals 0 up to 0, which does include f of 0. So if you start at 0 and stop at 0, if a is equal to b, maybe 0, then you get some value to your sum. Okay, so that's notation for sums. And then I have a proposition for you to do with sums. My claim is that for any natural number, again, look, I'm using this, any n in the set of natural numbers, but pronouncing it out loud, any natural number. For any natural number, the sum from 0 to n of the natural numbers is n times n plus 1 over 2, which you might have met before as the formula for triangle numbers. It's the sum of numbers up to n. But we're going to prove this with mathematical induction, just to look at what that looks like. So here's the proof. We need to say what the statements are, and in this case it's pretty clear that the statements are, well, the things in the question indexed by the number n. Mathematical induction needs your statements to be indexed by the natural numbers, so you need to find n in the question, I suppose. And clearly P0 holds because on the left hand side, when n equals 0, that's a sum that just contains 0. So it's not an empty sum, but it is a sum that just has the number 0 in, which then, if you add up all of the numbers, you get just 0. There's a subtle difference between an empty sum versus a sum with lots of zeros in it, but let's move on. So 0 on the left, and on the right hand side, if you plug in n equals 0, then you get 0 times 1 over 2, that's also 0. So statement's true, both these things are equal. Not an interesting claim, I think. P0 says the sum of the natural numbers from 0 to 0 is 0 times 1 over 2, but it's 0 equals 0. Okay, interesting step. We need to check that we can get from Pn to Pn plus 1. Proof by induction always works like this. You always need an idea for how you're going to get from n to n plus 1. It can be very complicated. Here, we're talking about the sum of the first numbers up to n plus 1, if we're talking about Pn plus 1, which is almost the same thing as the numbers up to n. So the difference, quite literally, is that last term of the sum. So if we're adding all the way up to n plus 1, then by the definition of what that sum notation means, that's the same thing as adding all the way up to n, and then also adding the n plus 1 term on the end, which here is just n plus 1, because we're just adding numbers together. So this is by definition of how the sum works. Okay, so then we get to use our inductive hypothesis. The power of mathematical induction is that we're assuming that Pn holds, statement Pn, in our chain of consequences. We're assuming that Pn holds and trying to show that Pn plus 1 holds. Which means that we get to use facts like the sum from 0 to n of k really is n times n plus 1 over 2. That's what we're aiming for, of course, to show that for all n, but here we're assuming it's true for a particular value of n. There's a subtle difference there. A particular value of n, Pn, now we're allowed to replace it like this. And then some algebra to go and replace that and rearrange it and show that, aha, this is now n plus 1 times n plus 2 over 2. But that's exactly what we wanted. This is the statement Pn plus 1, by which I mean that the thing on the left being equal to the thing on the right down here is the statement Pn plus 1. To check what the statement Pn plus 1 is, you need to go back and look at the thing in the question and imagine that it was n plus 1 wherever you see n. It's maybe helpful to write out the family of statements that we've got, but if you're interested in substituting n's with n plus 1s. Anyway, we've now checked P0, and we've checked that if Pn is true, then Pn plus 1 is true, so mathematical induction says that we can now conclude that Pn is true for all n. All right, all natural numbers, we can tell you what the sum from 0 to that natural number is. Okay, so there's a little example of proof by induction. Have a corollary. That's a maths word for something that follows from a bigger theorem or something larger. Usually it follows in quite a straightforward manner, sort of follow-up result, if you like. And this is a follow-up result not to that little thing about adding together the numbers, but a follow-up result to the principle of induction. So there's a lot of stuff on the board, but most of it looks the same as mathematical induction. Let's look at the hypothesis together. The idea is that if P of capital N is true, so if your statement P capital N is true, maybe capital N is some large number, and you know that one's true, and if you know that after that, if Pn is true, then Pn plus 1 is also true, then you get the induction effect, if you like. You get the chain of consequences from P capital N onwards. So the conclusion is Pn is true for all n greater than or equal to capital N. And in fact, the setup of this question, the stuff at the top, says that in this case, maybe you only have statements that are indexed by numbers starting at capital N. I suppose you might in general have maybe some other statements in there for n less than capital N where you're not sure if they're true or false or something like that. But the corollary here says that if you start with P capital N and you have the inductive step from there onwards, then everything's fine. All those statements are true from capital N onwards. And maybe turning it over in your mind a bit as we're talking through it, you've realised that that's pretty much exactly the same idea as induction. We've got a proof on the screen, the idea of a proof, and that's to translate this into the principle of mathematical induction, like it was in the theorem that we had on screen a moment ago. To do that translation, we need to find a family of statements indexed by the natural numbers starting at 0. So being a bit pedantic, the principle of induction says that your statements need to be indexed by the natural numbers starting at 0. And that's not quite what we've got, but we can make it precise by defining some statements. So these are sort of new statements, Qn, new statements, that we're building out of our existing statements, Pn, which I'll label up here. We have existing statements, which remember only hold from capital N onwards, but that's okay because they're my new statements, which are called Q. My new statements will be indexed starting from 0. I have Q0. It is, to be precise, Q0 is P capital N. Q1 is P capital N of capital N plus 1, and so on. And then I can prove these Q statements with induction, normal induction, because I have precisely P capital N is true. In translation, that means that Q0 is true. And this statement down here, it says for any n greater than or equal to capital N, but after translating, this turns into for any n greater than or equal to 0, if Qn is true, then Qn plus 1 is true. There's maybe a change of variables in there to get between the two, but that's the inductive step for the statements Q. And then I've got precisely what I need to prove the same as Q by induction, and then come back and say, aha, that means that the statements P were true from capital N upwards, because those are the ones that I'm talking about here. Okay, this is an example of how you can take a kind of intuition that this feels like it's describing something very similar, but then make it precise by setting up some sort of translation between the new problem and the previous problem that you had. Here I've been saying translation as if we're going between different languages, but it is also a literal translation along the number line if you have a geometric point of view on these things. Anyway, I also want to tell you about strong induction. This is maybe a different type of induction that you might not have seen before. I know that I hadn't seen it before I studied at university. It's a similar idea though, same aim. We're trying to prove that Pn is true for all natural numbers n, and it starts the same when we have this family of statements indexed by the natural numbers. We suppose something different though, but we suppose that P0 is true, but then we suppose that for any n, if P0, P1, all the way up to Pn is true, then Pn plus 1 is also true. So if you like, we look back at all the previous statements and use that to decide that the next one is true. So if it's true that P0 and P1 both being true, that together that implies that P2 is true, then that's an example of this inductive step here. And then maybe it's the case that once I know that all three of these are true, all previous values, then maybe that implies that this one is true. And the strong form of induction says that if you have that property, that whenever all previous values are true, the next value is true, together with P0 is true, then once again you conclude that Pn is true for all natural numbers n. And this works in the same way as induction. It's about looking back at the previous statements, and it's got lots of things in common, I suppose, but it feels quite different when you're using the strong form of induction. It really is just a different form of induction. It is under the hood the same thing as the principle of induction, and I'm going to prove that first. This proof is a little bit more abstract than the proof of the sum of the numbers, because I'm not proving a particular statement, I'm proving the thing in strong form of induction. That if you have both of these, then you get Pn is true for all natural numbers n. And perhaps confusingly, I'm going to prove that with normal induction. It's the same sort of translation that we had for that corollary just now. The same sort of translation to turn this into normal induction, except instead of being a geometric translation, it's a more metaphorical translation. Let's see. So here's the proof. We need some statements, and we need it to be true that whenever Qn is true, we get Qn plus 1. That's one of the hypotheses for normal induction. So I would like to get to this statement down here. To get there, my idea, I suppose, is that we define the statement Qn to be pk holds for all k up to n. So all of that stuff that's in the hypothesis of part 2 of the hypothesis of strong induction, suppose that's called Qn. So Q0 just means the same thing as P0. So if P0 holds, then Q0 also holds. So that translates across nicely. The hard one is convincing yourself that the thing in strong induction turns into this thing on the screen. So what do we have? In strong induction, we're assuming that if pk holds for all of these, then Pn plus 1 holds. So from here, we get that Pn plus 1 holds using the hypothesis in strong induction. So now if Pn plus 1 holds, then, well, what can you tell me about Qn plus 1? So Qn plus 1 is a big complicated statement. It says Qn plus 1, it says that the statement pk must hold for k equal to 0, 1, 2, and so on, all the way up to n plus 1. So let's write that out. Pk holds for k 0, 1, all the way up to n plus 1. But we have most of that already because we're assuming that Qn is true. And Qn covers all the cases up to n. So all we need is also the case n plus 1. And that's the one we get from the hypothesis in strong induction. So it's sort of using the hypothesis of strong induction to get Pn plus 1 and then bundling that back in together, adding it onto the list of things that we've proved. And Qn is the list. So strong induction gives us that final element, but then we're recombining it into a slightly longer list. That's the inductive step. That gets us from a list of length n to a list of length n plus 1 of these statements to do with P. And then we can use normal induction, because now we have Q0 holds, and we have whenever Qn is true, Qn plus 1 is also true. And that's the setup for normal induction. So we get our conclusion that Qn holds for all n. So as a result, it must be the case that Pn holds for all n, by the way, because, well, these Qn statements just include all of the Pn statements. For example, if you care about P37 in particular, then I suppose go and look at Q37, and the statement Q37 says, oh my goodness, P holds for all values up to and including 37. So good news, it holds for 37 or any other number that you're thinking of. This is quite good because it shows you that you can use normal induction to prove that the strong form of induction works. Going the other way, you might like to think about how you can use the strong form of induction, it's a bit more straightforward this way around, to prove that the normal form of induction works. So it's up to you. If you think that the normal form of induction is the obvious one, then this is a proof on the board that you can get the strong form of induction as a result. But vice versa, if you think that the strong form of induction is the obvious one, that you should be allowed to assume all the previous things hold in order to deduce the next one holds, then good news, you can prove that normal induction works, because that's like fighting with your hands tied behind your back, isn't it? Right, okay. Two quick definitions. I have a definition of what it means for one number to divide another. So given natural numbers m and n, we say that m divides n if there's a natural number such that m multiplied by k is n. There's some notation for this, which I'm not really going to use, which is that m divides n, written with a vertical line like this. And there's a definition of prime numbers on the board. Maybe you've met prime numbers before. A natural number larger than 1 is prime if no natural numbers except 1 and p itself divide that number p. Said differently, it's got no non-trivial factors, and it's greater than 1. Okay, so I have a statement involving prime numbers that I'm going to prove with the strong form of induction. So remember, strong form of induction says, well, if you check that p0 is true, and then you check whenever p0 up to pn all hold, that it's also the case that pn plus 1 holds, which sometimes feels easier because you're assuming loads in order to the weight of all of the previous cases, and you just have to prove the next one. Okay, here's the proposition. Every natural number greater than 1 can be expressed as a product of one or more prime numbers. This is something about factorization. Okay, so here's the proof. I suppose really I'm using the corollary that my statements are indexed by numbers starting from 2 and upwards, but that's such a small change that I'm trying to get away with it. So here's my statement as Pn, that n can be expressed as a product of prime numbers for n greater than 1, which is why I'm starting at 2. Anyway, clearly P2 holds, because 2 is a prime number. Exercise for the reader, check that 2 is a prime number using the definition on the previous screen. Okay, so that's our starting point. And then for a number that's greater than or equal to 2, suppose that, this is our inductive hypothesis, that the proposition holds for all natural numbers up to, but not including n, not yet. So now we're interested in the number n, sort of new one that we haven't looked at yet. Let's say, two cases, it might be prime or it might not be. If it's prime, then it's the product of just one prime number itself. The claim at the top here says 1 or more, so all prime numbers automatically meet this definition because they're the product of just itself. So there's the product of one prime number. If it's not prime, we're going to have to try a little bit harder. And crucially, if it's not prime, that means that it's got some non-trivial factor. There's some natural number that divides it, which I might call r, which means that we can write n as r times s. At the end there I have n as r times s, where those are both greater than 1. So now I've factorised my number. Of course, I don't know very much about those factors, r and s. They might be prime, they might not be. So if they're prime, then I'm done because I've written n as a product of prime numbers, but no reason to think that they would be prime numbers. I mean, numbers can have factors that are prime or not. But here's where we get to use the strong form of induction. We're assuming, by the hypothesis, that Pm was true for all m less than n, for all previous cases that the proposition was true. And that means that I have these smaller numbers r and s where the proposition is true. So by the inductive hypothesis, each of r and s can be written as a product of primes, and therefore n is also a product of primes. Just multiply them all together in one big product. So whether n is prime or not, Pn also holds. Pause here. Do you see how this is different from the normal form of induction in how it feels when you're using it? That you don't just look at the previous case, you look at all previous cases. And that can unlock different proofs that you might not have thought of, because if all of your inductive proofs always look at the previous value, then things like multiplication are really hard, because there's not much that the factorization of n tells you about the factorization of n plus 1. You maybe want to look at smaller numbers, in which case strong form of induction is helpful, because this has let us look back at all previous cases and use the fact that the statement is true on all of those. Anyway, by strong induction, we say that Pn is true for all natural numbers. They can all be written as the products and prime numbers. And that's the end of the proof, but I can't resist a side remark that the question of whether or not this is unique, the prime factorization that we've discovered here, whether or not we had any meaningful choices along the way about how we choose R and S and how we break this down into prime numbers, that question is much harder and is not covered in this course. Okay, I'd like to do some definitions now of things like addition and multiplication, because you can define these things recursively and it's got the same flavour as proof by induction as I look at it. So here's a definition on the natural numbers of addition, and it works like this. So I define it recursively. First I tell you how to add 0. I say that for any number m, you add 0 to it by leaving it alone. So m plus 0 is m. And then, if you're not interested in adding 0 but you want to add something else, my rule is that you can add a number m plus 1 by adding n and then adding 1. And that's a definition. So this defines, for example, 5 plus 3 by saying that, well, 5 plus 3, that's the same thing as 5 plus 2 plus 1, which of course is recursive because 5 plus 2 is defined as 5 plus 1 plus 1, and recursing further, 5 plus 0 plus 1 plus 1 plus 1. And then you get down to 5 plus 0, at which point you're allowed to use this first part to say, well, 5 plus 0 is just 5. So then I have in the brackets here 5 plus 1 plus 1 plus 1. And behind this definition, I'm supposing that you have names for all the numbers, that you know how to add 1. The definition of natural numbers is that every natural number has a next natural number that you get by adding 1. So for a full and proper definition, I should explain, I suppose, what adding 1 means. But if you've got some system of adding 1 in mind, then maybe you can get from that line at the bottom to the final answer of 8. This is a terrible way to actually do addition, but it's a good way to define addition recursively like this. I'm using the fact, I suppose, that every natural number is either 0 or it's m plus 1 for some natural number n. Those two cases, right? That 0 is a natural number, and then every other natural number is the successor of something. It's one more than something. That's the only ways you get to be a natural number. Okay, that's my recursive definition of addition. It's quite a lot of work to work with, as you've maybe already noticed. Let's go one more. So the addition that I've just shown you has some relatively nice properties. You've already met by working with addition of natural numbers, I'm sure. One of them is its associativity. So the addition is associative. So for any 3 natural numbers, x, y, and z, we can do this, which is maybe the least dramatic punchline of any proposition in these lecture notes, that x plus, in brackets, y plus z, is the same thing as x plus y in brackets plus z. And maybe this seems absolutely obvious to you, that you should be allowed to add in whatever order you like, but warning, there are operations out there that don't do this, where the order of operations matters, which one you did first, even though it's the same operation. Luckily, addition is nice, and addition has this property. We're going to prove it with induction. Of course we are. We're inducting on z. So first is the case where z is 0, and that one's not too bad to work with because you can use from the definition what it means to add 0 is to leave the number alone. So x plus y plus 0, which would be this thing on the left. I'm writing LHS for left-hand side, meaning left-hand side of the equation. So it'll be x plus y overall on the left, and on the right I would have x plus y in brackets and then plus 0 on the end, But my definition says m plus 0 for any m is equal to m, and that includes even if m is something fancy like open bracket x plus y close bracket. That's a natural number, so we can go from this being m to just have m plus 0 is just m. I've not written the brackets around the outside there. Putting these together, we see that both the left-hand side and the right-hand side are equal to x plus y. Now I've made a meal of that. I've said loads of words to justify why you can put 0 in two different places, but I'm trying to highlight that none of these steps rely on my intuition about adding or about being allowed to move brackets around. I'm only using the definition. In particular, I'm using the part of the definition about adding 0. And working very carefully. Lots of proofs that I've seen in lecture notes for other courses are laid out like this, where there's some sort of central idea that maybe we work outwards from it, or maybe we work from the left-hand side and the right-hand side inwards to get to the same thing in the middle. The proof is almost never, I think, developed by going strictly left to right to see what happens. That's probably not the order that someone had these ideas in to get from x plus y to, I should write brackets around that and put plus 0 on the right-hand side. Oh good, that's the right-hand side. But probably someone's working from each statement, each side of the equation, inwards. Probably. Often with lecture notes you don't get to see the working out that went into this. Maybe very little working out. There's a statement about the number 0. I'm preparing you to see the next slide where we do this in general to get from z equals n to z equals m plus 1. So we're going to be armed with our definition, which says how to go from adding n to adding n plus 1. That'll be useful because that's the recursive part of addition, and we really want to go from adding n to adding n plus 1, or at least we do on the right, where we want to add a larger value of z. We're inducting on z, we want to get towards larger values of z. On the left it's a bit more subtle, the adding z is inside those brackets, we're going to need to deal with that. But we're also armed with our inductive hypothesis, which, because we're doing an induction on z, we're supposing the proposition is true for z equals n, which means that if we see precisely the statement anything plus, and then in brackets, anything else plus n, we're allowed to move those brackets over onto the first two anythings. So we're proving quite good statements for each value of z as we go. Don't be distracted by the fact that this statement on the screen, in the basis case, is pretty rubbish. We're about to assume an inductive hypothesis that's quite strong. Here it is. And I've tried to label in each line which rule we're using. Let's quickly write out. So rule 2 in the definition, as a reminder, I can't remember if I had m's and n's or x's and y's, and I want to use it for several different things, so I'm going to write out that was something like a plus b plus 1 is equal to what you would get by adding a and b, but then one more. So that's rule 2 from the definition. Is this as a reminder, and the inductive hypothesis says that we can move brackets around if it's the number n as the third quantity. It sounds really specific, but there it is happening in the middle. Look, x plus y plus n, and we're moving those brackets. So on the screen it probably looks just like we're shuffling brackets around, but that's the beauty of a proof of associativity. It's all about where the brackets are. So on the left hand side, when z is n plus 1, we have quite literally all of this, I'm afraid, with all the brackets. And we might start by noticing that we have inside these brackets, we have something with a plus 1 on it. And our rule about how addition is defined lets us do that first switch to move some brackets over. The rules of the game here is we have to use the rules from the definitions or the inductive hypothesis. We're not allowed to use any other intuition about how addition should work as we go. So, okay, I can do that shift inside the brackets. And now what have I got? Well, I've got something else where I have, looking at the wider collection now, I have a number plus and then something plus 1. So now I'm sort of squinting, losing focus, so that y plus n looks like a single object, so that I can use this fact again, right? Now I'm thinking of that being the quantity b. So if I do that, then I have b plus 1, and I'm allowed to move those brackets so that plus 1 is on the end. If I do that, then I have this line here, where I've moved the outer brackets over. So now I read x plus, and then in brackets y plus n, and there's a plus 1 on the end, but that's quite good news, because I sort of think that the result of this calculation should be 1 larger, so I'm expecting a plus 1 on the end. We're adding a larger value of z. I'm not allowed to use that intuition, but I feel encouraged if I see a plus 1 near the end along the way. We've got an inductive hypothesis, so that lets us use this move to say that at this point in the proof, what we know is that addition is associative if the third number is n, and that's exactly what we want to do, to move the brackets over. And then finally, this is of the form a plus b in brackets and then plus 1, which, reading rule 2 the other way round, lets us shift just finally to move those outside brackets back over to the right, so that we have n plus 1 being the thing being added. The reason we're doing that is to move it so that we have precisely the quantity z, which is the number n plus 1, right there on the end. So all of that is z. So I started with x plus and then in brackets y plus z, and I ended with x plus y in brackets and then plus z, which is the thing on the right hand side. So good news, addition is also associative if the third number is n plus 1. And by the magic of proof by induction, we've shown that it's true when the third number is 0, and we've shown that if it's true when the third number is n, then it's also true for when the third number is n plus 1. Therefore, it's true for all values of z. And each of those statements included all values of x and y along the way. The thought here, I suppose, takeaway, that's the end of the proof. We have a square at the end of our proof here, at the end to indicate that we're done. But takeaway thought is that if your problem includes lots of integers, then you might choose one to be the one that you induct on, and make each of your statements include all possible values of the other ones. So might be how you want to roll things there. Okay, that is proof that addition is associative. You know other things about addition, I think, from your experience of adding together small numbers. For example, you know that addition is commutative, that the other order works. So if given x and y, x plus y is the same as y plus x, I'd encourage you to prove that using induction on y, to show that for any value of y, you can interchange the order of addition against any number x, but doing the induction on y, and that's on the problem sheet, so you can have a look at that if you like. Okay, quickly, definitions of multiplication and other things, just to show you that you can do recursive definitions for these things as well. I had multiplication in my introductory video, time to define that, I suppose. So my rule is you can multiply by 0, you will get 0. And then if you want to multiply by n plus 1, if you're asking about a larger number, n plus 1, then for any n, multiplying by n plus 1 means multiply by n and then add on m. That's my definition of how to multiply. This is pretty terrible as a definition goes in terms of practical applications. For example, if you want to do 5 times 3, then I can't use this rule because it's not 0 as the second number. I'd be looking at doing 5 times, well, it's 2 plus 1, isn't it? 2 plus 1. So that's 5 times 2 plus 5. And then, oh my goodness, this is a recursive definition. So I now have a time symbol in here as well. It's time to use, I suppose, the definition again. This is 5 times 1 plus 5 plus another 5. And then recursively down here, 5 times 0 plus 5 plus 5 plus 5. And oh my goodness, now I get to use the first part of the definition to say that this thing buried inside all of these brackets is 0. But it's not over yet, because We now need to look at the definition of addition. If we're going to add 5, well, adding 5 was also defined recursively as lots and lots of add 1s. So possibly if we now go through the definition of addition lots and lots of times, we can get to the answer of 15, but it will be at least 15 more lines of work. So I'll pause that to show that this is not a very practical definition, but does let you define multiplication on numbers. There's also something called factorial that you might have met before. I would define this recursively like this, to say that 0 factorial is defined to be the number 1, and then for any natural number n plus 1 factorial, you want a factorial of a larger number. Well, I'll define it by saying first work out n factorial, and then multiply by n plus 1. So you can make these recursive definitions which all have the same shape as each other, and all have the same shape as the natural numbers, and the same shape as the principle of induction. And that's not a coincidence, that all of these things are based around the way that the natural numbers work. I'd like to finish by showing you the well-ordering property of the natural numbers, which is written at the top there. It says that every non-empty subset of the naturals has a least element. By least element, I mean an element that is less than or equal to every element in the subset. So for example, the primes have a least element, it's 2, because 2 is a prime number and it's less than or equal to every prime number. The odd numbers have a least element, it's 1. The multiples of 10 have a least element. Any subset of the naturals has a least element. I'd like to show you what that's got to do with the principle of induction, so that we find another way of thinking about the principle of induction. Okay, so we're going to prove this by contradiction, but it's contradiction combined with the strong form of induction. So here we go. Contradiction means that we suppose the opposite and show that that leads to a contradiction, to essentially nonsense, which means that the only remaining case is that the thing is true. So we're going to suppose that there is a ridiculous object, let's find out, a non-empty subset S that does not have a least element. I'm saying ridiculous to help myself imagine that this thing is non-existent, so that I can start looking for the contradiction. Okay, we're going to define S star to be the set of natural numbers that are not in S. Later on in the section on sets, I'm going to introduce the idea of the complement of a set, but because I haven't introduced it yet, I'm doing a one-off definition here of something called S star, which is the set of natural numbers that are not in S. Okay, so S is one of these weird, ridiculous things, we hope to show, a weird, ridiculous thing that is a non-empty subset of the naturals with no least element. Okay, and we're going to use induction. We're going to induct on the natural numbers, and our statements are, well, Pn is the statement that S star contains n. Our aim here is to show that all of the Pn statements are true, which means that S star contains all of the values of n, which means that S doesn't contain anything, that it was an empty subset after all. Okay, so initial step, note that 0 is not in S because, well, it's supposed to not have a least element. 0 is less than or equal to all natural numbers. So if you put if you put 0 in the subset S, then 0 is definitely the least element of S. You haven't got anything smaller in there. There isn't anything smaller than 0. So in some sense, if my enemy is trying to create a non-empty subset of the naturals, then they really shouldn't put 0 in. That makes it too easy for me, because I'll just point at 0 and say that's obviously the least element of your subset. What are you doing? Anyway, okay, so 0 is not in S, so it's in S star. Good news, that means that P0 holds. That's the easy bit. We would like to now show that all other numbers are also in S star. We're going to use strong induction for this. So suppose that P0, P1, P2, all the way up to Pn all hold, which means that 0 is not in S, 1 is not in S, 2 is not in S, and all the way up to n is not in S. Now, n plus 1 can't be in S either as a result, because if it were in S, then it would be the least element. There isn't anything smaller because all of those statements hold. all of those statements hold, it means that there's nothing smaller in the set S. We've checked all of these small numbers, and now it's time to look at n plus 1, and no, we've agreed there's nothing smaller that's in S, so n plus 1 can't be there either. Otherwise it would now be the smallest element of S. So on our checklist of natural numbers, we conclude n plus 1's not in S either. So it's in S star, and therefore Pn plus 1 holds. Pn plus 1 being the statement that n plus 1 is not in S. It's in S star. And that's what we need for strong induction. We have P0, and we have the idea that if P0 up to Pn all hold, then Pn plus 1 also holds. And strong induction says that we can put those together to conclude that Pn holds for all n. So by strong induction, we're done. S star contains all of the naturals, S contains none of them, it's empty. That's a contradiction with the thing we supposed in the first place. So there's no such non-empty subset without a least element. Or said differently, without the double negative, every non-empty subset of the naturals has a least element. Okay, that's the well-ordering principle. And the proof here, which is over, the proof here has use induction. So you might think that this is a more advanced result, that we start by assuming induction and then we develop such fantastic results as the well-ordering principle. But actually it's a bit more subtle than that, because some people like to start with the well-ordering principle and then derive the principle of induction from that. So let me show you that. This is a proof the other way round, where we assume that the well-ordering principle works, that any subset, any non-empty subset of the naturals has a least element, and we use that to demonstrate that induction must work. So if you like, this is a proof of the principle of induction using the well-ordering principle. So we're coming full circle now. The principle of induction is one of the first things I showed you in this video, and we're now going to demonstrate that it follows from the well-ordering property. So this proof is a little bit difficult because we're not actually proving a specific thing about adding up the natural numbers to get the triangle numbers or something. We're proving that the conclusion in the principle of induction really does follow from the hypotheses in the principle of induction in general. So what we've got is we've got a family of statements, and we suppose that P0 is true, and we suppose that whenever Pn is true, Pn plus 1 is true. And then we're going to use well-ordering property to reach the punchline at the end that Pn is true for all n. Works like this. We're going to translate that problem, metaphorically, translate that problem into a thing about subsets of the naturals. Here we are. So we're going to let S be the set of natural numbers such that Pn is false. We're going to try and show that's empty, to show that Pn is never false for any natural number. So suppose that S were not empty, that there were some points. We get to use the well-ordering property working this way round. So we're using the well-ordering property here. That means that S has a least element. So we're allowed to move from having this nebulous idea that there's a whole subset of cases where Pn is false to a specific one, and in particular the least. So we're moving to looking at the least element of S. That's a very precise place to look. We're looking at precisely the first value of n such that Pn is false, using the well-ordering property. So, housekeeping, that can't be 0 because we know in the hypotheses of induction that P0 is true. So it's n plus 1 for some number n. Every natural number is either 0 or it's n plus 1 for some natural number n. And then if you write n plus 1 for the least element in S, because it's the least element in S, n can't be in S. So Pn holds. It's not in S. Pn is true. And we have the inductive step in our hypotheses for principle of induction. So we can get from Pn to Pn plus 1. So once again, the least element is n plus 1 in the set. We're supposing that all at once, and this is a proof by contradiction, we're supposing all at once that n plus 1 is Pn plus 1 is false, that Pn is true, and that Pn implies Pn plus 1. That doesn't work. if Pn is true and Pn implies Pn plus 1, Pn plus 1 must be true. The inductive step implies that Pn plus 1 also holds, which contradicts n plus 1 being in S. So supposing up here for contradiction that S were not empty, we've now reached a contradiction. You would have a least element, and then looking just to the left, but wouldn't that imply that that wasn't actually that? Oh, no. Okay, so S must be empty, and therefore Pn holds for all n in the natural numbers. So this is a demonstration that the principle of induction is equivalent to the well-ordering principle, well-ordering property. And you can use whichever one you like as the sort of fundamental truth, and then the other one will follow from it. So these aren't two separate things that you need as starting points for your theory of mathematics. If you've got one of them, then you get the other one. And if you like, this gives us a third way to think about mathematical induction, which is that you have a set where the statements are true. And I would like to say quite a lot more about sets in the next section. But before we get there, we have a proof of the binomial theorem using the principle of induction. I've split that out into its own separate subsection, so I'll see you in the next video for the binomial theorem.